Alright, so a couple of days ago I had this interview where I was asked about this problem and asked to approach it. So I thought this problem was very interesting not to share on my Twitter and talk about it. So I would be talking about what problem I was asked and how I approached it and ultimately solved this in the interview. So the problem is that there are certain nodes or certain resources in the AWS infrastructure that if they are spun sequentially, they take some considerable amount of time. And resources can have dependencies. That means that a certain resource cannot be spun up until the dependency has been spun up successfully. For example, here target group depends on EC2 and EC2 ultimately depends on VPC. So unless the VPC has spun up, EC2 cannot spin up, and unless EC2 has spun up, target group cannot spin up. So an algorithm was needed to be designed which would speed up this process of spinning up these resources and bring it down from 15 minutes to lesser time. So the model can be designed as a dependency graph. So we can design a dependency graph like this. So we can project the arrows of a node towards its dependency. For example, EC2 makes target group dependent upon it, and listener, and listener makes EC2 and load balancer make listener dependent upon them. So it's a simple graph structure. Now a node in this graph can be designed like this. So we will have a name, we'll have a resource type, we'll have the children for the node, and we'll also store the parents because we will be going to use this in the algorithm, and we will store that how many dependencies that this depend on have not been spun up yet. So for example, the children of target group are EC2, just EC2, and listener are EC2, load balancer, private link. So unless these spin up, listener cannot spin up. So we will have this information in the node data structure to track this information of which children have not spun up yet. So we can use a simple graph traversal algorithm like BFS or DFS to track the children length initially. And then how I look to solve this is by using a simple and standard graph algorithm, that is Kahn's algorithm. So first of all, if this graph has circular dependency, Kahn's algorithm will directly tell us that okay, the process number of nodes conflict with the number of nodes that we have traversed, so certainly there is a cycle and the structure is incorrect, so error. And if there is no cycle, then we can use an algorithm like this, where first we will identify the parents. So the information that what are the ultimate parents, what is the leaf. So here, I might have mixed it up. So the ultimate parents are these, but these are the things which have to be processed in the last, and these are the things which are the leaves which have to be processed first. So what we will do is the first run would be a BFS or DFS, because ultimately we will have to traverse this graph once in order to solve this. So we will traverse it, we will take the count of children, and we will also store the parents in a data structure like we have them stored here. So this traversal serves three things. First is it identifies the leaves which have to be spun up first, then it initializes the unmet dependencies or unspun dependencies with children.length, and then it also populates the parent data structure. So all good and all well till here. So we will push the leaves into a queue, and then as this has to be parallelized, we will use something like a triggerer and a worker pattern so that n workers can pull parallelly from the queue. So these two things will be pulled parallelly from the queue, and then after pulling the initial ones, we will see that if AWS has a tag. So for this is done to check that these don't get spun up again. So we will ensure that our whole system is idempotent. We don't want to spin VPC twice or thrice. So we will tag that in AWS so that it does not get initialized again. So this is for a performance optimization that we put an idempotency check. And after that, we will go to the parent and we will decrement the unmet dependencies. And if the parent has 0 dependencies left, that means cool, the parent can now safely spin up. We'll push this parent into the queue and then it will happen again. So the queue does not process each thing inside it synchronously. Rather than that, the workers pull the stuff from the queue parallelly. So it processes it very parallelly so that our performance does not get hurt. Now, this is what I was saying. This is a pictorial representation of what will happen. So wave 1, it will pull out VPS and DNS. Then wave 2, it will pull these 3 things in parallel. Then these 2. I think I messed up here because the dependencies will not get resolved like this. So I don't think these 3 will get spun parallelly because I'm pretty sure that load balancer has more dependencies than EC2. So okay, but I think the idea is clear and good. And third is that what happens that if the graph is still being processed, that means the spinning up is still going on and the server crashes. So in the interview, I came up with these 2 approaches, that we will snapshot the graph on disk and we will remove the large part of the data structure. But snapshotting is very inefficient because the graph data structure is huge and it will cause a lot of space complexity problem, and we will have to do frequent writes and it is not very good. It's inefficient. Second is we'll use AWS as the durable store. So tag, we discussed about tag now, so we'll use the tag. So AWS persists this for us. On restart, query AWS for tagged resources. All that is good, but the best solution which I got the hints for is the durable queue, which we will put in front of our provisioning service, that is our DAG. A good message queue will help us, combined with AWS tags, which will handle durability and idempotency. So yeah, that is the final architecture for this. So we'll have 3 durability boundaries for this, queues and AWS, and our service will be stateless. Yeah, that's it. I hope I did not go too fast and I made everything clear. So yeah, that's it.